Yes, hi everyone. My name is Denyz Melchor. I work at UCLA with Smadar Nows, and I have a plethora of collaborators at different institutions. I will be today hopefully showing you how we can produce repeated tidal disruption events using supermassive black hole binaries. And at the end of the day, I'll be talking about dynamics. Yay. So we've heard a lot about the observations of repeating tidal disruption events and partial tidal disruption events throughout the conference. I didn't update my slides based on what I've heard this week, but one of the exciting ones that motivated our work was the Assassin 14 KO due to its very short orbital period of 115 days, the flares, right? And so, what is the explanation? What are the dynamics that can cause these stars to get onto these very short orbital periods and not be fully disrupted is one of the questions we're trying to answer, specifically for disruptions that range between 115 days up to around 30 years, right? So your lifetime, hopefully. Well, the time you're doing your PhD, your career in academia. So this is our system that we're looking at. We're looking at a supermassive black hole and then a sea of stars around it. And, we heard a little bit about two-body relaxation yesterday, and it's just an exchange of angular momentum, scattering events, different stars interacting with each other, causing the orbit of a singular star to push in and be tidally disrupted when it crosses that tidal radius. And so the theoretical predicted rate is around 10 to the minus 4 per year per galaxy. Wonderful. Now, if we introduce a secondary black hole to this system with our stars and our initial supermassive black hole, we can now treat each orbit as a triple, right? So now we're introducing triple dynamics. And Grant gave us a beautiful introduction of the eccentric quasi leadoff mechanism, which is another mechanism that people have studied in looking at tidal disruption events. And this just basically tells us that when you introduce a tertiary, the inner binary exchanges angular momentum with the outer binary. And this also shows that there's an enhanced TDE rate, theoretical TDE rate that has been enhanced. And so how do we get two supermassive black holes at the center of a galaxy? Well, you all talked about it throughout the whole conference. Two galaxies merge, and so eventually there's going to be a certain time where we will have two supermassive black holes. And so if we look at the galaxy major merger rate, so galaxies with the same mass, I just learned this, similar mass galaxies merging, then this is a plot for the merger rate with respect to the redshift. These are illustrious simulations of this, and then observations are the little crosses. And we see here at low redshift that 1 in 10 and 1 in 5 galaxies have recent mergers, major mergers. But there are even more minor mergers, right? So our galaxies having very differing mass ratios, and we're seeing many more for these minor mergers. And that's great. Good thing you all are observing these things, hopefully. I'm using the data to create a system. All right, again, this is my system. It is a supermassive black hole with a sea of stars. We're tracking one star, and there's a secondary black hole. And you might notice something about the sizes of these black holes. We are tracking the TDEs happening around the less massive black hole. Right, so very different from some other studies. And the reason we do this is that when we look at the parameter space in which the eccentric quasi leadoff mechanism is the shortest, one of the shortest time scales, or one of the shortest mechanisms happening the fastest around the differing black hole masses, so the disrupting black hole versus the perturbing black hole, we see that when the disrupting black hole mass is larger than the perturbing black hole, then we are not getting stars to be disrupted, right? And so this dashed line is the one-to-one on this. And the reason for this is because the precession due to GR and the stellar potential suppresses EKL. So, let's look at some time scales because I am a dynamicist. So let's look at This is the time scale with respect to the semi-major axis of the star. This is two-body relaxation. This is the eccentric quasi leadoff mechanism, just kidding, and the GR precession. And then for like this region in the parameter space, the eccentric quasi leadoff mechanism is shorter. And so we compare this to the two-body relaxation timescale, it's orders of magnitude longer, right? So this tells us that EKL is happening at a much quicker rate, or not quicker rate, it's happening sooner than two-body relaxation, because two-body relaxation is often a diffusive process that happens over longer time scales. And this is for different stellar density profiles, so something more core-like versus something more cusp-like. And, you know, so why do we care? Well, this is comparing them when two-body relaxation is a description of energy, while the other ones are a description of angular momentum. But if we compare just the angular momentum description of both of these, the angular momentum changes, then we can see that two-body relaxation and the eccentric quasi leadoff mechanism are much more comparable. And so with this, we've decided to combine these two mechanisms. So now we're combining the eccentric quasi leadoff mechanism with two-body relaxation. So we're taking into account the interactions with the stars as well as the gravitational perturbations from, or the exchange of angular momentum between the two different orbits. All right, now I'm showing you one of our simulations. This is an evolution of a star, right? So this is our system again. It's a star, black hole, black hole. So this is the evolution of one star with just the eccentric quasi leadoff mechanism. So it's just the exchange of angular momentum between these two. I'm showing you here in the semi-major axis of the star, its pericenter, and the inclination, the mutual inclination of these orbits. What do we see? Something extremely boring, right? It's exactly what we would expect. The eccentricity is changing, right? So it's becoming more eccentric, less eccentric, right? As expected, nothing fun. Wonderful. But now if we introduce two-body relaxation into the same system, so now we're combining EKL and two-body relaxation, and we're seeing a difference, right? So for the same exact parameters, we're seeing a suppression of these eccentricity excitations, right? So there's no longer this wobbling of the star's orbit up until a certain point. This happens because two-body relaxation suppresses the EKL excitations, and then it allows it to go into a parameter space in which it turns on. And then we get very exciting excitations of the orbital period. And, you know, right here, I didn't mention it in the last slide, my bad. This is the tidal threshold we have, right? So it's 2 times the tidal radius. So at this point, we would expect something to be tidally disrupted, partially tidally disrupted. So when our stars cross into this region, we can say we have now created a partial disruption, and because its semi-major axis has decreased so much, if we calculate the orbital period, if it continues at the semi-major axis, we can say it is around 8 years, which is very short. And also the inclination of this system has flipped almost 90 degrees towards the end of its evolution. And we do this for several thousand simulations. I'm gonna take you through it because there's a lot of little dots. Okay, in gray, so this is 1 minus the final eccentricity of our systems over the semi-major axis of the star. In gray, we have our initial conditions, right? That's where they start. In blue, these are stars we consider to survive. These are stars that basically remain in similar regions where they began. In the pink ones are stars that are they kind of got scattered off. We'll call it that. And then these green points are the ones that have crossed their tidal threshold. So these are all we'll consider TDEs, right? And I'm comparing, this is specifically to a mass ratio of 10, so our smaller black hole is less massive than our larger black hole, remember? And then we're comparing this between a more core-like versus a more cusp-like stellar density distribution. And these particular stars right here, we've picked out these because they graze this tidal threshold, and they're on, if we calculate their orbital period, they would be on periods of 30 years or less. For you all, thank you. So we've done that, and okay, sorry, spoiler. All right, so these would be our potentially repeating tidal disruption events. These are our candidates. So if we calculate the expected number of repeating tidal disruption events per their orbital period in these systems, then we would match up pretty well with some of these observations, but I didn't include any new ones, and maybe these are old, but wonderful, right? So, and then this is a comparison with the Hills mechanism, which I know has been studied previously to describe repeating tidal disruption events as well. Okay, this is our rates, right? So here I'm showing these different colors represent our different binary black hole eccentricities. So the eccentricity of the binary, the supermassive black hole binary, and we're comparing this for our core distribution and our cusp distribution for our different mass ratios. And then we're comparing it as well to the average observed rate and the observed post-starburst rate. And so our rates for something more core-like, they match up pretty well. For something more cusp-like, they're slightly elevated. I hope that's cool to you. And so if we actually look at just the number of disruptions per supermassive black hole, this is a description that this is something that we created prior to introducing two-body relaxation. So just in your minds, imagine this going just up a little bit, right? And so this is, this would be the TDEs coming from the smaller black hole. And we compare that to, this is with respect to the disrupting black hole mass. And we can compare this to tidal disruption events created from a larger from the more massive black hole. And the tidal disruption events would probably be happening due to chaotic orbital crossing, and they're very similar for mass ratios of around 10. And we can compare this also to two-body relaxation within around 100 million years. And as we can see, for a more massive black hole, EKL tends to dominate. And with that, getting us out early, we combine the eccentric quasi lead-off mechanism with two-body relaxation. It can naturally lead to these repeating tidal disruption events and hopefully produce some similar rates to post-starburst galaxy rates.
All right, yeah, you're first to the mic.
Thanks. Do you have a distribution of the periods, of like the repeat times that you expect? Or just, but qualitatively, like, what's the tip? You said 30 years, you mentioned the one simulation you singled out was 8 years. What's the, how are they distributed?
Like this, right?
This
so
okay.
It's around 10. Yeah.
Okay.
Yeah.
Okay. Thanks.
Yeah, thanks for the great talk. I'm wondering, for your initial distribution of stars, is that already an outcome of two-body relaxation, or is it coming from something else?
Can you repeat your question?
Yeah, so basically what I'm thinking is that you're arguing that this dynamical process is happening on shorter time scale compared to two-body relaxation. But do you assume when you have a number of stars, the distribution, is that already an outcome of two-body relaxation only, or it's from, so how do you determine the distribution of stars, the initial distribution?
Do you remember? I don't remember.
But you're working on doing like a time simulation.
Sorry, Brenna was one of my collaborators.
Yeah, no, for this one, they're just pretty like simple cusp core, like power law profiles, but you could certainly imagine starting it with different distributions.
Okay, I'm just saying that if they are the outcome, well, maybe they're not, but if they are the outcome of two-body relaxation only, then basically it is so there are slightly cyclic arguments, right? Because you need to have this process happening faster, then that will actually change your initial distribution, but after that.
Well, it depends. I mean, in principle, these are started at, or are kept, the binary parameters do not change over the course of these simulations, but you can imagine in a real scenario, you have this slowly inspiraling binary. So there's a lot of things. So basically in this first case, there's just like a variety of profiles chosen.
Okay.
So more steep or less steep, but
Okay.
in reality, I think that probably the time evolution of the binary and its slow stripping of the outside of the stars would have a bigger effect.
Okay, thank you.
Hi, great talk. Have you been able to, specifically with the core versus cusp, the two density profiles, have you been able to make like a distribution of betas in each case, like the impact parameter?
No.
I don't know. Sorry.
Yeah, we'll talk about it. 'Cause
Thanks.
yes and no.
Maybe you mentioned this before, but how exactly are you doing these things? Is it, you're not using n-body, right? You're
I'm
doing
not
some,
using n-body. Yeah.
is it like some secular approximation?
Yes, it is.
How does it work with two-body relaxation as well?
So we introduce two-body relaxation via kicks, and the kicks are introduced on the phase space of the orbit, and so typically they would be introduced mostly at the apoapsis.
Okay, and how often do you introduce these? Because two-body relaxation timescales are much longer, right?
I think every orbit.
Okay, is that physical?
You tell me.
Okay, sure.
I
We'll
don't
talk about it later. Thank you.
Oh.
Just one question, follow-up. This is really interesting. Are you thinking about the potential for starting maybe with what is observationally possible to detect and seeing whether or not it might be measurable given your predictions? So in terms of both line of sight offset in the spectroscopy, the motions of those nuclei, or on the sky separations and things like that, some combination of phase-phase?
That would be interesting. I would like to work with an observer because I don't know much about it.
Okay. All right, let's thank our speaker again.